Hello, everyone, and welcome to the June 2022 meeting of the Howard Astronomical League, known as HAL, H-A-L. And the meeting today is being recorded, and you will be able to view it at a future time on our YouTube site. And with that said, it's great to have everybody here. We have a really good meeting planned for you again tonight. And let me start out with a little bit of our regular thing here with our little astro humor. Give you a chance to take it in. Because everybody's muted, I could, it mutes all the laughter that's going on, but I see some smiles going on there. So I do want to thank those of you who submit the astro humor, because after doing this for 3 years worth of meetings, it becomes harder and harder to find new stuff. So I always appreciate when you send me the emails there. So that was great. Let's get that one there. And I'd like to welcome everybody officially here. And if we have any new members, unmute yourself and introduce yourself. Any new members today? Just so everybody knows, we're over 360 individual members, and of that, about 250 are family membership units. So it's really a big deal. We've grown by about 60% since the beginning of COVID. So that's a large amount of growth. I know we have some guests here tonight. So if you just want, any of the guests want to just unmute yourself and introduce yourself, not our speakers, you'll have your chance. Okay. Just go ahead and unmute yourself and say hello.
Okay, hi, my name's Chuck Kaloya, and I'm a guest of the Dutillies tonight. I live over in Frederick County, but I guess you still let me in.
Yes, we do.
Okay.
Yeah. We are equal opportunity, even for people in Frederick County.
Okay.
So thank you. Welcome.
Thank you.
Anybody else?
Hi, I'm Sherry Brown. I am Dominic Alfinito's mom.
Oh, welcome. The proud mom is here.
Yes,
all right,
indeed.
Dominic, no pressure.
No pressure. That's why I turned off my camera, actually.
She'll love you anyways. So, all right. Anybody else?
Hi, I will introduce myself real quick. I'm Dominic Alfinito's very proud research advisor. So it's nice to meet you, Mrs. Brown. And I live right here in Howard County in Columbia, and I'm a planetary scientist, mostly studying the moon at the Applied Physics Lab, also in Howard County. Okay,
very cool. Well, welcome. We hope to see everybody. Now that these meetings are on Zoom and they're going to remain on Zoom into the future, it doesn't matter where you're from. You could join at any time. Any other guests that want to introduce themselves?
Yeah, hi, we're the Kramers. We're friends of the Hemowitzes, and our son Matthew is a student at the school with Dominic, and we're very excited to be here tonight.
Well, we're excited to have you both. Welcome. Anybody else? Going once, going twice. All righty, so welcome everybody. Thank you very much. We're going to change up the format a little bit from those of you who are regulars from what we usually do, where we go into a bunch of news and different things. I'm going to just talk about the star parties a little bit, and then we're going to get right to our guest speakers, and then we'll follow up with some of the business after the speakers, because we're honored to have two special presenters today. So before we jump right into them, though, I just want to let everybody know that our next star party is for members only, which is June 25th, which is a week from this Saturday. And hopefully the weather will be just as good as it's supposed to be this Saturday. I know there's some impromptu requests going on, and we'll see if somebody wants to open up. I won't be able to do that myself this Saturday. And then July 9th is our next public star party. So, and I'm very happy to say that the telescope in our observatory, which is known as HALO, Howard Astronomical League Observatory, is working great. And thanks to everybody who's been really working hard to get all the new technology working properly, and so everybody can enjoy it. Let's see. And went wrong way. There we go. And then once again, I would like to, even though I'm the person that's kind of in front of you all the time in these meetings and in a lot of events, but there's a great crew here of officers and committee chair people that do a lot of great work behind the scenes and in front of the scenes to make the club run. Everybody's volunteers, and we really appreciate everything they do. So I want to just once again thank all of our chair people and our officers very much for everything. Without them, we wouldn't be doing this, as well as all of our past officers who are still volunteering. So tonight, we're going to jump right into our presenters. And the way this works is they're going to start presenting. Dominic, just let us know if you want to take questions while you're presenting, or if you want to wait till the end. If you can put your questions in chat, I'll try and watch them. Yvonne's not here today. She usually watches for me, but we'll do that, or you could just open your mic up and ask the question. So let me just give you a quick introduction to Dominic. Dominic is a senior at North County High School in Glen Burnie, Maryland. He will be graduating next month. Congratulations. He has been a very active member of the mock trial team as well as the astronomy club through his high school career. Dominic will be attending college at UMBC, which is not far from where I live here, and many of you probably, and he plans to study physics with an emphasis in astronomy. And I'm going to let Dominic talk about his honor that he had in presenting what he's about to present, and talk a little bit about that, as well as his topic, which is the possible causes of hydration of Vesta's Oppia, if I pronounce it correctly, crater. And with that said, Dominic, I'm going to stop sharing my screen, and you could start sharing your screen. And welcome and thank you for presenting tonight.
Thank you. I don't hope to command applause or anything, but I actually graduated on the 8th this month. So.
Oh, great.
All right, I guess I'll get right into sharing my screen. You all can hear me, right?
Yes.
You can see the presentation?
Yes.
Awesome. All right, so my topic again is on hydration of Vesta's Oppia crater. And I just want to start off by thanking Dr. Parvati Brim here. I work with her over the course of this year on the student research project through the Lunar Planetary Institute. And specifically their program over there is XMASS, which is exploration of asteroids and the moon for secondary students. So I'll get right into it. So if you guys haven't heard before, like, what's Vesta? Is that something from Star Trek? Well, no, it's actually an asteroid in the main asteroid belt. And in fact, some estimates take it as around 9% of the total mass of the asteroid belt. It is the second largest asteroid in the belt, second only to Ceres. So it's pretty big, although the asteroid belt is only about 3% of the mass of the moon. So in the grand scheme of things, it's not all that big, but it's pretty large. It's differentiated. So Vesta actually has a crust and a mantle and a core. It was visited back in 2011 by the Dawn spacecraft, where it stayed for around 14 months, I think, until it moved on to Ceres. That being said, all the data I used in my research was through Dawn, so I don't think there's anybody that worked on Dawn here, but thank them because they put together a really impressive mission, and I used their data from about a decade ago. So 6% of all of the asteroids that we've seen in our solar system are actually pieces of Vesta. So these are little bits that have been broken off over previous impacts, and we now observe them as smaller pieces, and sometimes they actually visit us on Earth in the form of meteorite impact. So we call these V-type asteroids, and they can be matched up through their spectrum and based on their composition. So why exactly do we care about hydration on Vesta? Well, water is key to life. That's pretty clear. Understanding the movement of water in the early solar system is key to understanding how water got here to Earth, right? And Vesta is in between the outer planets and the rocky planets. And in the early solar system, there's a lot of infall of perhaps hydrated impactors. For example, we expect the Earth perhaps to have been visited by comets or other things that deposited water on Earth. So understanding how Vesta was hydrated is applicable to a great understanding of our solar system. More recent data from Dawn has shown that Vesta possessed water. However, we thought for a really long time that Vesta actually was just bone dry. We knew that Ceres is pretty hydrated, but we thought Vesta was just bone dry. But more recently, Dawn data has shown that to really not be the case. So where do we look for hydration on Vesta? Well, I looked specifically at Oppia crater. Now you can see here on this topographic map that shows one of the hemispheres of Vesta that Oppia crater there sits along a boundary between a really low-lying groove and a really high, well, a moderately high spot. So Vesta, unlike larger bodies, it's quite a spheroid. So it's not, it's not a spherical thing. It's very oblate. So there are very deep grooves that occurred when Vesta had its south pole pummeled. But it also has mountains that are far taller than Mount Everest. So there is a really big variance in terms of topography on Vesta. On Oppia specifically here, if you look on the bottom right in that map, that shows a absorption, or rather a infrared mapping of the area where Oppia crater is, with it centered in that red dot there. And you can see to the northwest, there is an ejecta blanket from Oppia. And I was curious, why is there this very strong ejecta blanket in this area? Because this area actually has been thought for a long time to be a pretty globally devoid area for hydration. So what could have caused this hydration at Oppia crater? Well, some recent, relatively recent analyzations of Dawn pictures show that Cornelia crater, for example, has guiles, which would indicate actually surface flows of water, ancient water. So maybe it was surface or subsurface hydration from long ago that was there before the impactor formed Oppia crater. Or maybe it was a hydrated impactor. Maybe it was a chondritic meteorite that struck Oppia, what's now Oppia, and formed the crater and also deposited its hydration there. And with that, I go on to how do you determine hydration? Well, I used two main methods in my research. First of all was molecular absorption spectroscopy. So that sounds like a big mouthful, but really all it means is that certain all molecules absorb and reflect light differently. Think of it a little bit like a fingerprint. Every molecule has a unique absorption spectrum. And specifically, what I looked at is the 2.8 micron range of light that is absorbed by both water and hydroxyl containing minerals. Now, this isn't material that you'd think of as just, just ice in its, or water in its current form, but it's part of the mineral structure. And so this is in the mid-infrared range. And again, this data was taken using the instruments aboard Dawn. Now, the absorption spectrum is only useful for the first few millimeters of regolith. So this really only tells you what's going on very close to the surface. The other thing that I looked at is hydrogen neutron.
Dominic, could you explain what regolith is, please?
Sure. It's basically the pulverized material that sits on the outermost layer of Vesta, and pretty much any other rocky body, like the moon, Mars, anything that has a fine powder that was created over eons of impacts is regolith. Speaking of regolith, the other thing I looked at, again, is hydrogen neutron abundance. So neutrons are basically created by active galactic nuclei, quasars, the sun. They're everywhere, and they're a very abundant source of ionizing radiation in the universe. And one of the unique properties about them is their interaction with hydrogen atoms. So you have neutrons that come in from these sources and they go into regolith, and they undergo what's called moderation. So neutrons that are being emitted from cosmic sources are moving around the speed of light, not quite the speed of light because they have mass, but they're moving at a good percentage of the speed of light when they enter regolith. When they go through regolith, the hydrogen that's present will slow them down, kind of like going from moving through air to moving through like maple syrup. They're slowed down, and when they exit, they're going closer to the speed of sound in terms of scale. And so this is a form of remote sensing you can do to detect the abundance of hydrogen atoms within a regolith. And this is sensitive to the first few meters of regolith. So this, you could look 10 meters down, 5 meters down into the regolith and sort of look deeper down into what's going on at that sublevel. So what did I find when looking at this? Well, if you see in the top right here, this is a comparison of relative elevation, and below it is the band depth of the 2.8 micron band that I looked at. And this is drawn along that, if you saw earlier, I'll go back to it. This is drawn along that northwestern edge of the ejecta blanket of Oppia in that light section. And you can see that as we go up the outer slope of the crater, and up here, I don't know if you can see my mouse or not, but up towards the very tippity top of that top graph at the crater rim, you can see that actually the abundance of hydrated material increases at the surface level. And I also looked again at the subsurface hydration from neutron abundance, and you can see in the bottom left graph now that the surface band depth sits far above hydrogen abundance. And what we found, me and Dr. Prem, was suggestive that actually it was not subsurface hydration, but in fact a hydrated impactor that formed this, because most of the hydration is at the surface level of regolith, on the outside of the slope. And we also found that what most likely occurred that formed that sort of unequal distribution of the ejecta blanket to the northwest there is that actually the most common angle for most impactors to occur is around 45 degrees. And it's also noteworthy that where Oppia crater sits is a pretty steep slope edge. So the impact occurred along imagine like the side of a large cliff face, but not quite that extreme. So that's all the slides I have. Again, I'd like to thank Dr. Prem for helping me all throughout the year doing this research, and also Ms. Heimwitz with organizing it. And if anybody has any questions, I guess I can take some.
Dominic, why don't you take a moment, please, and explain the award you received, the presentation that you were able to give, and how you give. This is what kind of brought you to our attention.
Sure. So as part of the XMAS program done through the Lunar Planetary Institute, I was part of several student researches being conducted all across the country. I believe it was 5 other schools that ended up fully participating in the program. But we each submitted an abstract that was and a poster that was reviewed by a panel of judges. And then we gave a oral presentation in sort of a competition form that was voted upon by the judges, and mine was determined to be the most satisfactory, I guess. But they liked mine the most. So I was awarded a trip out to the University of Colorado Boulder to be part of the CERVI conference, the Explore Science conference over in Boulder. Normally it's done through NASA Ames, but since COVID started, this is their first time returning back in person. So I will be going out there July 17th.
Congratulations.
Thank you.
Awesome. Your presentation was really awesome also. So what did you, what got you from the research that you did you find anything, what was your expectation and where were you surprised? Or was your expectation spot on from the beginning?
Well, I kind of chose the XMAS program allows students to choose between whether they want to research lunar science or focus more on asteroids. And well, I figured I know less about asteroids, so I should probably study that so I could learn something. In fact, I learned a lot about how to conduct remote sensing data research and using spectral analysis techniques to figure out like what's going on here. And it really surprised me that you can sort of determine, surface chemistry and petrology on asteroids just in your office, just by using like accessible data. So I kind of walked in having only the expectation that I know nothing and that I ought to learn something. And I learned a lot, so.
Well, that's great. Anybody have any questions for Dominic?
Yeah, Phil, I have one.
Go right ahead.
I missed what is detected in the subsurface impact, deep impact. What exactly is sensed?
Right. So we're looking at essentially when neutrons enter regolith, they are slowed down during their interactions with hydrogen atoms. And essentially, the more hydrogen atoms that are present, the more that they are moderated, and it changes the properties when they reach a detector on a space probe. So normally that abundance is, I believe it is expressed in something like cubic grams per mole of material or something like that.
What is it? Does the hydrogen that's impacted by neutrons emit at a particular wavelength?
I believe that there could be gamma emission through excitation, but I believe what we were only looking at through the data was the neutrons being moderated, and then they basically are redirected back up. So they go into the regolith, they are slowed down, moderated, their properties are changed, and then some of them come back up and then go to the detector on the spacecraft.
Oh, okay. Thank you.
Okay, so we have some hands up, so we'll go with Daniel and Dave and Arjun. So Daniel, unmute yourself.
Question for Dominic. With that Vesta asteroid, do you think it'll be possible people could live on it, or you could ever someday they could ever send astronauts to work on that asteroid?
One day maybe. I think that we would probably, in terms of mission, go to somewhere that has like lots of useful metals or something. But I definitely could see a sample return mission like what we had with OSIRIS-REx, sending something up there, collecting a little bit of Vesta and bringing it back.
Yeah, because there's now this Artemis mission where they're going to be, in a few years, they're going to be sending astronauts back to the moon, and they're going to, on the South Pole, and they're going to put a woman on the moon for the first time. And I think, what are they going to do? Hopefully, see if they can extract water and they can use it to do the same thing we do here on Earth.
Well, Daniel, the nice thing about Vesta is that it actually shoots bits of it at us. So you can actually buy pieces of it on eBay for a couple $100 if you really wanted to. So
Is it possible?
We get a natural sample return too.
It would be interesting to drink the water on that asteroid.
Yeah, I'm not sure if it's quite in the amount or form that you could really drink it.
Would taste good.
Well, Daniel, if
so.
we get enough, you'll be the first to bottle it. Hey, so thanks for the question, Daniel. I'm gonna put you back on mute and go to Dave. Dave, you're up.
Yeah. Congratulations on an impressive project, Dominic. My question was, how applicable is this technique to other cratered bodies, specifically the moon? With all the findings of water there. I mean, is this used generally for bodies like that, or are there limitations to this technique?
Actually, so for Mars specifically, they use well, I'll back it back a little bit. We rely, for example, on the neutron abundance on natural sources of neutrons from like distant sources like cosmic rays or the sun. For Mars missions, what they actually bring, what's been suggested, I think it might have been brought on some missions, is actually a source of neutrons from like a photon neutron generator, a PNG or something like it's called, and they just stick it right next to the soil and collect their data there. So both of the techniques I used are pretty common in planetary science research and brought with them on spacecrafts.
Yeah, that's very cool. Thank you.
Thanks, Dave. Arjun, you're up.
Okay. So in terms of hydration on water bodies, do they have to form by some other hydrated body hitting the surface of a dehydrated body, or could water form based on chemical reactions like ions, isotopes, or something like that?
Right. So one of the questions I started this research with is, could space weathering have formed hydroxyl radicals from water-containing minerals that could be detectable in a spectrum? So hydroxyl is just oxygen and hydrogen bound together with a single negative charge, and it's commonly caused when essentially H2O or some other material has that other hydrogen broken off of it. So I had the same question actually about, could some sort of stellar interaction have caused a change in the geochemistry of the surface? But specifically for this, the two questions I really settled on were, well, was the hydration already on Vesta and then something hit it, or did something hit it that brought the hydration? And the result was, we think more likely than not, it was actually a hydrated impactor that hit a quote unquote dry body. But hydration just means there's hydrogen atoms present in whatever is there, really.
Right. So from analyzing the spectrums, are you somehow able to put a time on when that hydrogen, on when that hydration would have appeared on Vesta or some other body?
I don't think it's really sort of a time sensitive technique, because you don't see any like fluctuations in interactions or anything like that. And obviously it's not going to have any like, radioisotope dating or anything like that. So I guess you would just be looking at the local makeup of the area, seeing any physical changes in it and sort of back tracing it. One of the things I did look actually is on Oppia crater. I don't know if you can see it. Can you see my cursor?
Yes.
There's these two smaller craters that lie just on the edge of Oppia crater, and we know that those actually occurred after Oppia crater formed because they interrupt the crater rim. And so I also was researching a little bit into these two smaller craters and if they influenced the spectrum.
Right. Well, thanks very much. Hey, so we're gonna move on to William, but Dominic, if you could hang on till the end of the meeting, which go past a little past 9 probably with the questions maybe. And if he has additional questions, we could jump right in. Yes, Michelle.
It looks like William had a question that he typed into the chat.
Okay.
So I thought
great. Okay,
Yeah.
great. Go ahead, William.
Yeah, this is really, really impressive work, especially for a high school student, Dominic. So thank you so much for presenting it. My question was just towards the sort of the impetus for your work that you were speaking through the first few slides. Do you know if this detection of this sort of the angle of this impact and the delivery of water into this the impact site, does it have any implication as to the rate of delivery of water into the inner solar system from the outer solar system?
I'm not sure. I guess you'd have to do a more generalized survey of hydrated impacts or just impact craters that display a hydration feature on Vesta or Ceres or any other rocky body that may have intercepted a downfall of those hydrated impactors coming from the outer solar system. And then sort of, set it within a time frame of the light heavy bombardment around that and then see if, how what was the frequency of these coming in. So
totally. Thank you so much.
It was just great. And Dominic, if you want to unshare your screen,
Yep.
then we'll be able to share his screen. And I do want to say, this is really exciting, having you as a high school student. And I'll introduce William as a PhD student right now. And, we're used to having a lot of seasoned professionals. And what that means is people with gray hair who have been doing this for a long time in their areas of specialization. And having both you, Dominic, and William at your young ages, really being experts already in your field and being part of our present presenters, historical presenters here at HAL is just really exciting. And the youth movement and the science is very well, is very good, very healthy. And that's very good for everything, for in the real world as well as in our hobbies here. So thank you very much. So let me introduce William real quick. So William Ballmer is a, oh, hang on, let me get to a slide here. Let me just, are you sharing yet, William? Oh,
No, I was waiting. If you'd like me to share now, I
I'll
can.
put my screen up here with you up there.
You got it.
There you go. Hang on a second. I got to move this one out of the way so I can see what's going on. There we go. There we go. William is a PhD student at Johns Hopkins University and a graduate research assistant at the Space Telescope Science Institute. He and his colleagues researched the growth, evolution, and composition of giant planets, brown dwarfs, and very low mass stars using some of the world's largest optical and infrared observatories. WYN 3.5 meter, the Magellan 6.5 meter, the Gemini 8.1 meter, VL2 8.2 meter, the VLT interferometry array, and soon James Webb Space Telescope. If you go to the website in our meeting section and you go to William's section down here, today's speakers, you'll be able to see a link where you could go right to his page, which I've been to a couple of times, and it's very interesting. And I learned a few things, and that's where I grabbed a couple of pictures. So, Dominic, back on yours, if you remember your thing there, I was glad to see I grabbed the same picture of Vesta that you were using. So I had the right thing. But anyway, so William, we're thrilled to have you here. Thank you for presenting to us today. And I'm going to stop sharing here, and it's all yours.
Well, thank you so much. And I want to thank Bob as well for inviting me. It was really great to meet him at Balticon earlier this past month. And thank you guys for having me here. So I will share my screen. And you guys can see the full screen presentation now?
Yes.
All right. That was a great introduction. So I'll just get right into talking about directly imaging exoplanets. And I've got a treat for you in the title slide because we're already seeing an image of an exoplanet right here. It's this little blob. And I'm sure that all of you as amateur astronomers understand a little bit better than the general public how difficult it is to see faint things next to bright things, and how impressive it is when you finally, are able to reduce an image, find the thing that you're looking for, and you show it to someone else, and it's a couple of pixels or it's a smudge on a spectrograph, and the person says, "Great," and you're like, "It's the thing. This is the thing." So just a little bit of table contents. Some bookkeeping for this talk. I'm going to walk you through some science background, and then some of the instrumentation and data processing that we do in direct imaging. And then I want to speak about some of the observations that have already been made in the field, and then a little bit about what I do, and hopefully open it up for some questions and discussion. So to start off with science background. The challenge in direct imaging, like I said, is the contrast ratio between, for example, Jupiter and the sun is analogous to the contrast ratio between a firefly next to a lighthouse. It's around 1 billion times brighter the sun is than Jupiter. And And the angular separation between the two is like trying to see that firefly a foot away from that lighthouse from across the continental United States. So we have two sort of challenges, two fronts at which to attack this problem. We need improved angular resolution, and we need improved contrast in all of our images. But the reward is probably the most rich data set that you can get on a planet outside of our solar system. When you directly detect a planet, you can measure its spectrum. That can tell you something about the temperature on the planet, clouds, the presence of winds and storms. You can measure elemental and molecular abundances, which open up a whole suite of analysis that you can do. You could even try and detect signs of life, or measure the glint from surface water oceans, or measure greenhouse gases. These are all obviously projected measurements that you could make, but the potential is there. And really the only other method that can get you some of this information is called transit spectroscopy. But transiting planets aren't very representative of a sample, and that doesn't unlock all of the measurements that you can make when you directly detect the photons from a planet. You can also determine the planet's orbital motion, and you can analyze its stability within its orbit. You can measure resonances and zones of influence within the system. You can measure perturbations due to other planets or other bodies within the system. And by linking up both of these analyses, you can try and really dig down and investigate the evolution of the planet in its orbit, the evolution of the planet's chemistry over time, and try and peer way back and understand how it formed, and maybe that tells us something about how we came to be. So I'm going to perform the cardinal sin of all exoplanet talks and show you the plot. But exoplanets have very dramatically changed our view of how planets form. This plot, which I think is shown in almost every exoplanet outreach talk I've attended, plots separation on the x-axis and mass of the detected planet on the y-axis. And this really tells us more about our ability to measure planets and detect them than it does about anything about planets themselves. But you can see here the transiting technique is great at finding close-in planets. The radial velocity is very adept at finding also close-in but slightly more massive planets. The microlensing technique is probably the least biased, but it has a very low occurrence rate. And then direct imaging up here is in a very oddball zone. It is currently able to see very massive planets at very wide separations, and it's unlike any of these other detection methods. So the great thing about these detections is that because they're so unlike most of the solar system planets that we know and love, our planet formation theories have to explain both our own solar system and our own occurrence and all of these other things. So what do we call an exoplanet? According to the IAU, I'm deferring to authority here. The IAU says that an exoplanet is an object that doesn't burn any nuclear fusion at its core. So specifically, it limits the upper limit of a planet at 13 Jupiter masses, which means that the pressure and temperature at the planet's core is not sufficient to fuse deuterium into helium. Deuterium is a heavier isotope of hydrogen that's slightly easier to fuse than hydrogen is, but much less abundant. It's something that orbits a star, a brown dwarf, or a stellar remnant. And it has to have some mass ratio. So it has to be smaller by some degree than the body that it's orbiting. And then we use the same minimum mass that we consider within our own solar system. All of these have caveats, and I would say that this definition, to put it lightly, created conversation within the exoplanet community. Anecdotally, I think an exoplanet is something that's low mass, not really a star, that maybe once formed or currently orbits a star. That's my working definition. And like I said, I have a bunch of caveats for all of these things. So, you know, what do we call an exoplanet? Who is we, right? There's no actual IAU approved definition of an exoplanet. This definition is a working definition from a commission circa 2018, and the topic was so contentious that the IAU didn't want to vote on it. You can see I've given the definition for this mass. So you want something that's around at least 25 times less massive than its parent body. And again, this this term here, definition of minimum mass in our solar system, comes with a whole can of worms that I'm sure our Pluto enthusiasts know very well. So I want to talk a little bit about stellar occurrence and then planetary occurrence as well. So we know that there are fewer big stars than there are small stars. And we also know that that turns over in the low mass regime, so that there are fewer low mass brown dwarfs, or objects that are too big to be planets by that IAU definition, but too small to burn hydrogen at their core. That leaves us with the most common type of star being these things that are right around the hydrogen burning limit, these TRAPPIST-1-like systems that are around the 10th of a mass of the sun. And we also know, interestingly enough, that giant planets are much more common around high mass stars. There are only a handful, I think maybe 2 or 3 giant planets that we found around M dwarfs. And we think this is because higher mass stars have more planet-making material around them when they begin. And you need a massive amount of planet-making material to form giant planets. So there's some point at which a star is not massive enough to pull enough material in a disk around it to form giant planets. This is just showing you where in this sort of occurrence plot these brown dwarfs lie. And then when we're talking about planet occurrence, and this is obviously only our current view with that imperfect population sample that we have, but we do know that there are more small planets than there are big planets. That goes for giant planets and terrestrial planets. As you go down in mass, you find more and more small bodies. There seems to be a peak in planet occurrence at around 5 astronomical units. So around here in this diagram, that means that there are very few close-in hot Jupiters, even though the transit technique has dredged up a ton of them. And there are very few far-away systems like that we see with direct imaging, and that there are a lot of systems that are very like Jupiter. And we also know, it follows sort of from this statement that these massive and wide separation planets that we can see with direct imaging currently are very rare. I wanted to speak a little bit about the planet physics side of this. So planets give off most of their light in the infrared, and because they don't have a source of nuclear energy, they cool down over time, and therefore young planets are much hotter and brighter than old planets are. This is very similar for brown dwarfs, and you can kind of see in this plot, which tracks age on the x-axis and the brightness of the target on the y-axis. These blue stars, once they start burning hydrogen at their cores, they maintain their brightness for all time. Planets cool very slowly for almost their entire lifetimes. And brown dwarfs are able to burn deuterium for a short amount of time at the beginning of their lives, and they sort of plateau here, and then they monotonically cool, just like planets do. So,
William,
yep, go ahead.
Victor has a question.
Yes, Victor.
So when you do this direct imaging,
Mm-hmm.
you're not looking at light that's reflected off of the exoplanet from its sun. You're looking at direct black body radiation from the exoplanet? Yep.
So that's a really great question and a very important point. So most of the direct imaging, if not all of the direct imaging that we've done so far, is thermal emission from the planet itself. So these are the planet's photons exiting it due to black body radiation, passing through its atmosphere, and then reaching us. Soon, we hope to build an instrument like LUVOIR, a mission concept for the 2040s, that will observe invisible light and potentially see that glint or the reflected light from the star bouncing off the planet and reaching us. So it's a possibility, it just hasn't been done before due to a number of technical challenges. So none of the stuff that I'll talk to you today about will be about that, but that's definitely something to keep your mind on when you're thinking about direct imaging in the future.
Okay, thank you.
Yeah,
So
totally.
we were to follow on to Victor's question there.
Yep.
Does that mean that the exoplanet relative to the star is off the edge and not in front of it when you're able to get that?
Yep. So when you're observing,
you lost in the,
yep,
right?
When you're observing in reflected light, there's a phase component. So when the Just like when you're observing the moon around the sun or an asteroid, whatever portion of the orbit that the planet is currently in gives some dependence on how much light you receive. So that's another prospect in direct imaging that people are really interested in is when we go out to try and find exoplanets, we lose a bunch if we are observing randomly and in short periods of time because we're seeing, planets in many different orientations, many of which will be inopportune phase alignments.
Thank you.
Hi, William. We have another question from
Yeah,
Arjun.
go ahead.
Go ahead, Arjun.
Yeah, I don't want this to take too long, but in terms of imaging, since you image exoplanets, is there specs to the camera which you use to image, such as bit depths, and gain, stuff like that?
Definitely. So there's a lot of very sensitive calibrations that go into both producing and then maintaining and operating the cameras that we use for direct imaging, because most of them are infrared sensitive cameras. There are actually a ton of extra considerations that you have to take into account. We take darks and flats and biases just like everyone else. We wake up and we put our pants on one leg at a time. But then you have to worry about well depth. You have to worry about sky glow if you're observing on the ground. You have to worry about how your camera reads out in the infrared, and especially, like you mentioned, the bias level or the background amplitude of the camera. So the infrared sensitive cameras are very fickle instruments, and there's a lot that goes into considering how you use them and how to not to break them.
Okay.
And another question from Dave. Oh, I'm sorry,
Yep.
Arjun. Did you have another question?
Oh, okay. So in terms of cameras, as far as amateur astronomy goes, the maximum bit depth for a camera is about 16 bits. But then for your types of planetary observing, is there more than 16? Is there like 18 or 20 or so on?
That's a good question. Most of the cameras that I've used, even the infrared cameras, have a 16-bit depth as well.
Go ahead, Dave.
Sure. When you were talking about solar system structure,
Yes.
when you talk about AUs, are we talking about the same AU?
Yes.
Yeah. Okay. So it's an absolute value from system to
is.
system. Okay.
Yes, so we like to reference everything back to our own solar system. So an AU in this context is the same distance, the average distance between the Earth and the Sun. We'll talk a lot about these exoplanets in terms of Jupiter masses, Jupiter radii, the brightness of Jupiter, et cetera. So we'll reference a lot to solar system properties.
Okay. Thank you.
Totally. So if we take a little bit of a step back, really, this is our goal, right? Is this simulated image of the solar system. We want to find something that resembles our own Earth, maybe resembles our own solar system. And we want to find a handful of them so that we can answer questions like how common are liquid oceans and biosignatures and all of these, projected measurements that we might be able to make. How common are Earth-like planets in general, and what do the nearest terrestrial planets look like? And all of these feed into these big questions that we're all asking ourselves. How did we get here? I ask myself all the time, how are planetary systems arranged? How do planetary systems form and evolve over time? But these questions are near impossible to access with the current operating technology that we have. The Earth has a contrast of about 10 billion times fainter than the Sun. And that contrast is decades, if not multiple decades away from us. So that means that if we want to image systems that are analogous to the planets in our own solar system, we need to really develop direct imaging techniques. And that means that we have to practice direct imaging wherever it's applicable and be continuously improving all of our methods, trying to improve our technology as well as our methodology. And I want to sort of take a step back and get up on a soapbox about what this kind of has to do with that plot that I showed you of all of the planets that we've detected so far and that definition of exoplanets that I gave you. Because wide separation massive planets are rare, and we're not sensitive to any of the other planets that exist. With our current technology, we have relatively few direct imaging discoveries compared to other methods. Some people take this to believe that direct imaging is less successful than other exoplanet discovery methods. The discovery methods that we do have are very weird. They're strange systems that we don't have any analogs to in our own solar system, and that are very low occurrence rate environments. Most are high mass and near the deuterium burning limit, or maybe there are low mass brown dwarfs that didn't form like exoplanets that are sneaking into our sample somehow.
William,
Yes, go ahead.
this is Bob. I have a question.
Totally.
One of the things that I have read is that much of the exoplanets that have been discovered are very close to their stars.
Very. Yeah.
And have a day or days revolution around their star.
Yes, that is correct.
So what if you have if you think there's an exoplanet there, and it's like even a large exoplanet, which they've discovered that's within like Mercury's orbit.
Yes.
And it's going around its star at, 15, 20 hours.
Totally.
How can you really make a lot of investigations about that planet when it's so close and going so fast?
Totally. That's a great question. So that's something that I think is really where the methods like the radial velocity technique and the transit spectroscopy technique excel. For a lot of those systems that are super close in, we see the planet pass in front of the star, and you're able to get fairly detailed observations of that planet's atmosphere because the planet itself absorbs some of the light from the stellar host, and you can compare what the spectrum of the host star looks like out of transit to what it looks like in transit, and infer what the planet's atmosphere might look like. So like you said, for those kinds of super close planets, we can actually get fairly detailed observations. The problem is that the chance of a planet transiting goes down very rapidly as the planet goes out, or as you have longer and longer period planets. So we can't use a lot of those same techniques as reliably or as frequently, because the planets take much longer to orbit and therefore to transit, for planets like the Earth or like Jupiter. So to answer your question, I would say that for those super close planets, we can actually make fairly detailed measurements because of their proximity to their star. And it's for these longer period things that we're having a lot more trouble.
Thank you.
That's a great question. Yeah, thank you. So to just again, stand up on my soapbox, I want to make the pitch to you guys to just embrace the weirdness of a lot of the objects that we look at with the direct imaging technique. A lot of these things in dark blue aren't even planets by the IAU's working definition. Maybe you have something that forms like a planet from a disk, but during its runaway gas accretion phase, it grows past 13 Jupiter masses and begins forming deuterium at its core. By that definition, we'd call it a brown dwarf, but it formed more like a planet than it did like a brown dwarf. Or maybe one of these things forms more like a star or a brown dwarf from a giant molecular cloud, but is much less massive than 13 Jupiter masses, and then is captured gravitationally into an elliptical orbit around a host star. We'd call that thing a planet nominally, but its formation pathway and its evolutionary history are radically different from any of the planets that we understand here. So we're in a very murky gray twilight zone when we're talking about directly detected planets. And there are a lot of really fascinating and nuanced science questions that you can ask about all of these different kinds of objects. And there's a lot to look forward to in direct imaging. But that nuance gets flattened out when your funding scheme or when public interest is only, cares very strictly about things that we can call planets with some authority behind that definition. So in my work, I observe all kinds of different objects across mass and radius boundaries. And I have a certain philosophy about what, really makes a planet. But my pitch to you is that you should ask yourself what these direct images can tell you about how the universe works, whether it's exoplanet dynamics or brown dwarf composition or star formation. And remember that each one of these observations, even though it might not be of a planet by its strict definition, is a really big step forward towards trying to observe another Earth.
Hey, William.
Yep.
I may be getting ahead, and if I am, just let me
Yes,
know,
sir.
and I will wait till later in the presentation.
Totally.
We were very fortunate here in our club, having some exoplanet expertise here.
Yes, definitely.
With Dennis Conti and some of the other presenters we have, and we've been really kept up to date on, from almost the beginning of exoplanet research and
Totally.
how did this, the discoveries fundamentally, are they potentially Earth-like
Totally.
planets, things like that. And then you've just taken this to a whole nother level. And so that leads to my question, which is, when James Webb started
Yes.
doing its exoplanet research, and this
Totally.
is where I may get ahead of your presentation here. So going beyond just trying to find more exoplanets, if you go back and look at the ones that you've already started researching, what are you looking for James Webb to validate or
Totally.
show
That's a really great question. So and I'll touch on some of this actually in this next section. James Webb is a 6.5 meter telescope, so it's actually smaller than some of the largest telescopes we have on the ground. What that means is that it's not as adept at seeing the closest regimes of separation that we can probe with direct imaging. What James Webb is really good at is its sensitivity. Because it doesn't have to compete with an atmosphere, and because it's operating in a range where planets are their brightest, it's operating in the infrared. James Webb will be able to make really precise measurements. And that's actually why I'm the most excited about it. It is not the potential of detecting new directly imageable planets with James Webb, because again, those will just be more of these weird outlier edge cases, but really trying to understand the planets that we do currently observe. And some of the planets that I'll show you in section 3 are cycle 1 targets with James Webb that I'm involved in, that are really, really exciting in terms of understanding how silicates and grains form in exoplanetary atmospheres, and understanding the compositions of different elements in those atmospheres. So what I would say is that that's actually the primary thing that I think most direct imagers are the most excited about, for at least for cycle 1. When we see what it can do, it might blow us away, and we might be finding new planets out the wazoo. But what I'm, the most interested in, and what I think the most promise is for really characterizing and understanding the things that we know about today.
Okay.
So just a little bit, and I'll go through this a little fast, but I wanted to talk about the instrumentation that we use in direct imaging, and how we're able to achieve those separations and contrasts where we can actually see planets and observe their spectra. So to measure closely separated objects, like I mentioned, you need a high angular resolution. And resolution depends on this equation. We have theta, which is the angle that you can resolve two sources of light into separate components. There's a constant term, and then you're looking at a direct proportionality with wavelength and an inverse proportionality with the size of your telescope. So this has a couple of implications for direct imaging. When you go out to longer wavelengths, you need a bigger telescope in order to maintain the same resolution. Cooler objects like planets emit their light at longer wavelengths, and therefore to observe planets at their most optimal contrast, you need a very big telescope. And like I said, to measure faint objects, you need to improve the contrast of your optical path. So if a 4 billion year old Jupiter, like the one in our solar system, is 1 billion times fainter than the sun, I'm just showing you some notation that I might commonly use throughout this talk. And a 4 billion year old Earth is 10 billion times fainter. If we go back to my Firefly and Lighthouse, the Earth is a speck of bioluminescent algae compared to the Firefly, compared to the Lighthouse. If we wrap in some of what I was saying about cooling tracks and how planets cool over time, then a very young Jupiter is around 1,000 times brighter than present day Jupiter. So it's only 1 million times fainter than its host star. And another star, an M dwarf, maybe 10 or 20 times less massive than its primary, would be around 100 times as faint as the primary sun. So these are some of the contrasts that we're thinking about when we're observing things with direct imaging. Now, putting large infrared telescopes into space is difficult. You might have heard that it took around 20 years for James Webb to get up into the sky. And that's for a number of reasons. Rocket payloads are limited in size, operations are very expensive, and we're very worried about breaking things that we send up into space. So in order to increase the diameter of our telescope in that equation and achieve the best angular resolution, we usually have to operate telescopes, at least the most massive telescopes, on the ground, which means contending with the atmosphere. You all know this probably even better than I do. But a larger telescope is more affected by the atmosphere because the incoming wavefront from our source is disrupted by more pockets of seeing than for a smaller aperture. For a small enough telescope with large enough seeing, you're not actually limited by the atmosphere, you're diffraction limited. But for a large telescope, you can fit many multiple seeing elements across your diameter, which means that the wavefront that you get is distorted to where you can only resolve something that's as big as the astronomical seeing. That's a really big problem if you have a 5-meter telescope and you're limited to that has a diffraction limit of a very small number, and you're limited to a seeing of 2 or 3 arc seconds. So we use a set of tools called adaptive optics to correct for the atmosphere's contribution. Light comes in as distorted plane waves, and we have a wavefront sensor, some black box that tries to measure that distortion compared to a flat, perfect wavefront. And then we send that distortion solution to a deformable mirror, which is a nice piece of glass that has a bunch of pistons behind it. We try and deform the mirror so that it cancels out the incoming wave and gives us a flat corrected wavefront. And there's some sort of feedback loop at play here. So you're only as good at correcting these wavefronts as you are at refreshing the deformable mirror. And I've hidden throughout a couple of these slides the sort of amount of contrast that we can improve when we employ this technology. So you can try and play at home and keep track of how much contrast we're actually able to drill down, at least with the current state of our technology, with these next techniques that I'm telling you about. So here's a really great example of adaptive optics operating at the galactic center, where there are lots of different stars. And when the adaptive optics are off, you have a very blurry image that's seeing limited. And as the control loop is turned on, you get impressive resolution. We also can try and physically block the light that's coming on axis down our telescope. You put your thumb in front of the dome. That's usually frowned upon, but you could do it and try and block as much light as possible from the host star. So these are coronagraphs, and they're optical elements that help us try and block out the center of our images in order to see faint or diffuse emission off axis. Modern coronagraphs are very complex. There's a whole cottage industry of people whose job it is to consider new and theoretical designs for these things that exploit how light interferes with itself along the optical path. But this is an example image of the Saxo coronagraph at the SPHERE instrument on the Very Large Telescope in Chile. And you can see that this coronagraph still lets in some of the light from the center source, but has suppressed this dark hole around the center of the image that achieves a very favorable contrast for viewing exoplanets.
I have to tell you that coronagraphs for the amateur are virtually non-existent. I have been researching for a long time.
Yeah.
And with the advent of H-alpha telescopes and stuff, there's no real market for them. But they do offer, a coronagraph does offer something that, you
Definitely.
know,
Yeah.
in viewing that you can't see any other way, but you can't find one for an amateur. They're so dangerous. If you mess them up, you're going to blind yourself.
They're especially dangerous if you're doing eyepiece observing. I agree. And the same goes for adaptive optics. I've been looking for a while for a company to come out with an adaptive optics system I could put on the campus telescope, because Baltimore seeing is not incredible. But I've yet to see an affordable adaptive optics solution on the market. So the last thing that I want to talk about is the post-processing of our image. So we have a number of tricks, both in our observational strategy and in post-processing, that we can do to try and remove excess starlight. You can imagine if you have a very stable optical system, the point spread function, or how a star looks in your images, it should be the same between different astronomical scenes. So if you have some reference star that you don't think has planets around it, and then a system that you're trying to find planets in, you could take a picture of one and a picture of the other and subtract the two and isolate the light from the planet. This is pretty difficult on the ground because the atmosphere is changing what our point spread function looks like all the time. But it's really adept in space. So for the James Webb Space Telescope, this is going to be one of the primary tools that we use to achieve good contrast in our images. We call these techniques differential imaging. And there are a couple of fun fun subgroup techniques of differential imaging. One of them is angular differential imaging, where we turn the rotator of our telescope off so that we center the star, and the PSF, which is just a function of the optical path, doesn't change over time, but the entire astronomical scene rotates around that central star. Because the central star is unchanging, you can median combine all of your images, which erases all of the off-axis light, leaving you with a good model of what your central source looks like. And then you can subtract that from all your images. And because the Earth's rotation and the movement of the night sky is a solved problem, you can derotate all of your images and stack them in order to reveal as much of the astronomical scene as you can. So this is a fun schematic of that. In a similar way, because the point spread function of your telescope changes with wavelength, if you're observing in multiple wavelengths and multiple filters, for instance, or if you have what's called an integral field spectrograph, which basically gives you an image for each wavelength along the spectrograph, you can monitor how the point spread function changes over time, not over time, but over wavelength channel. And because the source of the planet will not change its position over time, you can recreate the point spread function, subtract it from your images, and try and achieve a bit more contrast that way. So I wanted to show you basically what's the result of combining all of these techniques. So this is the SPHERE instrument going from seeing limited here to adaptive optics limited, and then to coronagraphic. And you can see the adaptive optics already give you a hint that there's a binary star within this system. And then when you block the majority of the light from the central with a coronagraph, you can really see the binary companion here at a high signal to noise. This is a sort of same schematic, but for the Gemini planet imager, going from seeing limited to adaptive optics to coronagraphic, and then with post-processing down to planetary. And if you were playing the game at home, this is about 10 to the -5 or 10 to the -6 in terms of contrast. So we're approaching around 1 million times fainter than the host star. And if you remember back to our sort of relational scale, that gives you the ability to see objects that are maybe young Jupiter analogs. So now I'll talk you through and show you some pretty pictures. This is really, I think, the best part of this talk is getting to see all of the exoplanets that we're able to see so far. This is the poster child not only for directly imaged systems, but for exoplanets. This image pops up if you go to the Wikipedia page for exoplanets, period. This is the HR 8799 system. It's a system of 4 super Jupiters, which are multiple times the mass of Jupiter, that all orbit their own star at distances further than the distance out to Neptune. So it's a very extraordinary system. And I have an orbit movie here from my collaborator, Jason Wong, that shows our observations of the planets over time. And you get a little orrery effect where we can really see them moving over about 10 or 20 years of baseline. So this is, I mean, this is the cake for doing this research. These images and these movies are really what it's all about for us. Another system here is Beta Pictoris, with the caveat that this is part 1. So Beta Pictoris B is another system that was discovered in around 2008. And it consists of a giant super Jupiter that orbits within the debris disk of a larger star. And here's, again, another orbit movie. So this orbit is almost, is basically inclined at 90 degrees with respect to our line of sight. So we see it orbit along this axis of the disk here. Here is 51 Eri B, which is the lowest mass exoplanet that we've yet directly imaged. It's around 2 to 3 times the mass of Jupiter. And it has a sort of an oblong eccentric orbit, which is unlike Jupiter in our solar system. So here's its orbit movie. This is really my favorite system of all of these that I'll show you today, mostly because it's the lowest mass, but also because its spectrum and its composition are radically different from the other exoplanets that we can directly image. And then a couple of still images. These are recent discoveries in the past 2 years from the WISES survey. So here you actually have a brown dwarf and a super Jupiter in the same solar system. And then here is WISES 2b, which is another super Jupiter. And the interesting thing about these systems is that the primary stars here in both cases are both solar-like stars. So these are both stars that are similar to our sun, but they host planets many times the mass of Jupiter. We can also directly observe the sort of forerunners of exoplanets, and these are called protoplanetary disks. They have features that we think are indicative of small unseen planets that carve these gaps and rings. This is from the radio telescope ALMA, and here's some images of protoplanetary disks from VLT Sphere. And another poster child of the direct imaging field is PDS-70. PDS-70b and C are 2 protoplanets. So these are planets that are still growing. And you can see that they're embedded within a disk of circumstellar gas and dust. The system is only about 10 million years old only. And these planets are hoovering up the material within that disk and growing in mass. One of the great things about a system like PDS-70 is that we can actually detect emission that tells us how fast it's growing over time. So this red dot here is part of a 2-color image, the red being visible light, H-alpha emission, just like you would do when you're observing a pretty nebula. And the blue is infrared emission that you saw in the last couple slides. And this H-alpha emission is from the superheated hydrogen gas that is falling onto the planet as it moves throughout the disk. So the planet is gravitationally pulling in this hydrogen, heating it up and producing H-alpha emission. And we can use some scaling relationships, some physics to translate that into a rate of change of mass over time, which is a really fun measurement.
You had my attention. Now you really got my attention.
Isn't that, yeah.
It's hard to comprehend. So
Yes.
first, how far away is the system?
This system is, I couldn't say exactly, but most direct imaging systems are around 50 to 150 parsecs away.
Okay.
So in terms of light years, parsec is what, 3 light years-ish. So yeah,
So
that's around the scale that we're operating at.
So that to help with that, I asked to put this in kind of perspective there. So any kind of change.
Yep.
Is, I mean, you've been giving some pretty minuscule numbers to begin with. Now we're even talking a different scale.
Exactly.
And how could you get enough data?
Yeah.
You know, it's like measuring the grains of sand inside a grain of sand.
Yeah.
To make that kind of determination is this.
Totally. I mean, so we observe these, I mean, these images, I say images, but they're stacks of images, data cubes of, you know, thousands and thousands of images that we take over the series of multiple nights on the largest telescopes that, you know, exist. So we do get a low number of photon counts, especially in individual images, but over time we're able to build up enough signal to make these measurements with, you know, a statistical degree of uncertainty is what I would say. But that's a really great point. I mean, at some points you're hunting individual photons from planets, you know, in some of these images, and it's really something when you're able to actually robustly, you know, with all of the statistical caveats, say this is what we see, this is what we're finding in this system. And that's one of the primary challenges actually of direct imaging, is being able to, you know, be so robust in what we are able to conclude from sort of a lower sample size of photons than other people have access to. So this is a quick and pretty plot of the motion that we've been able to observe since the discovery of these 2 planets in, I think they were discovered in 2018. So already in just a few years, we're able to see a nice amount of orbital arc from these systems. I don't have an orbit movie specifically for this system for you, but in lieu of that, I wanted to show this. And then this came out this year, and this was really something spectacular. This was in the New York Times, actually, this image. But just recently, Miriam Benisti, who is a French astronomer, was able to use the ALMA radio array and detect an excess of dust around one of the planets in this system that indicates that there's a disk within a disk. And what that tells us is that there's enough planet-forming material, or I should say, there's enough moon-forming material around one of these planets to comprise a number of regular moons similar to the Galilean moons. So we expect that these circumplanetary disks, like we detect here in this emission, are how you get moons like the Galilean moons around Jupiter. So this is the first, yeah.
Arjun has a question.
Arjun, yes.
So this is going to refer back to some of your previous teachings and some of the more recent images.
Totally.
So I was able to see that in many of the images that you showed in protoplanetary disks, that it's very dusty. And so thinking of it, might the dust affect the contrast in your image?
That's a really, I mean, that is an expert question, and you are absolutely right. So if you've noticed, I've only actually shown you one example of a protoplanetary system, and that's these 2. And if we work through some, I don't know, selection effect questions here, what's different about this image than, say, some of these images? And it's that this one has a huge hole in the center that these planets have been able to carve out over time. So we're really seeing this system in a snapshot where it's managed to clear out enough of the gas and dust to unobscure the protoplanets. And the protoplanets are themselves large enough and massive enough that they're bright enough for us to detect. So the reason that you don't, for instance, see protoplanets in these systems is that the planets that could be responsible for carving these gaps and rings in the disks are much too small to be able to emit enough light for our current technology to detect them. So that's something that's actually really interesting about these systems, is that we're getting indirect proof of planets' existences before we're able to find them in these earliest stages. So that's a very expert question. There are a couple of ways that we can try and hedge our bets against, how much of the emission from these planets is coming from, say, gas and dust that's in between us and them, and some, population level statistics that you can try and do with some of these results to understand the bias there. But I don't have anything definitive to say to you about that, because it's a very ongoing area of research.
Okay. Thank you very much.
Of course, thank you. So I want to talk very briefly about what I do. I don't want to run up against time here, but it fits within sort of the context, and my hope is that over the next couple of years of my PhD at Johns Hopkins here, we'll able to investigate even more of these systems, and this work will evolve even more so than what you see today. So one of the things that I'm really interested in is binary star systems. And it's because when I was 4, my parents told me that I was finally old enough to watch Star Wars for the first time. And I sat down with a big bag of popcorn, and I saw this, right? And it's Luke Skywalker on the desert planet Tatooine, which is a relatively habitable planet around 2 stars here. And what I see now when I think about this image is I see, oh, that's an A-type star and that's an M dwarf, and there's some orientation angle between these binary stars here and the horizon. So maybe there's some inclination going on in the system, right? So this is something that I tried to investigate with my most recent paper. We have here a system of an A-type star and a directly imaged M dwarf here, and they're surrounded by this massive circumbinary disk. So this system is only about 1 million to maybe 5 million years old, so it's very, very early. The planets within the system, if they did exist, haven't finished forming yet. And the system is very intriguing because, like I said, we have sort of a binary sunset like Tatooine, but we see this sort of dearth of material in the sort of habitable zone regions of this system, right? We see all of the material in the system is pushed to this outer rim here. We want to understand why. So the 2 stars in the system, like I mentioned, are surrounded by this disk, but it appears as if maybe this binary companion is disturbing the planet forming regions of the disk in some way. Part of my work was sort of pushed along by these hydrodynamical simulations that the team did, showing that if you have a binary star within a circumstellar disk, if the binary is inclined with respect to the disk, so say if the binary is swooping throughout the disk as opposed to rotating as the disk rotates, that it can generate these really dramatic spiral structures and a large hole within the center of the disk. So we see, something that resembles these simulations in the system, and we want to know, okay, what does the binary orbit look like? So what the conclusions of my paper were when I measured, when I directly imaged the binary over time, when I fit the orbit of the system, was that the binary orbit is in fact misinclined with respect to the outer disk, and it seems like our expectations were correct. I have a orbit movie here because I want to be like Jason when I grow up. But this is the orbit of the images, some of the images that I was able to fit over time with an orbit. And our conclusion is, like I said, that this binary system is truncating the habitable zone planet forming regions of this system. This is one of the few direct pieces of evidence that we have that suggest a broader theory of circumbinary planet formation, that planets around binary stars can only really exist, can only form even, if they are within the same plane of rotation and orbit that the binary system is. So when you see a binary sunset, like on Tatooine, you have to assume if it's inclined with respect to the horizon, perhaps, that that inclination is due to the tilt of the planet and not the inclination of the orbit itself, because otherwise the planet would not have been able to form. So that's some of the work. Another piece of work that I'm doing is on the PDS-70 system and a couple of other similar systems that actually suffer from what Arjun mentioned more robustly than PDS-70. So I work with a team who use the Magellan telescope and the Magellan adaptive optics system to try and measure these planet formation growth rates in different protoplanetary systems. And we have a paper that's coming out relatively soon on a survey that we conducted over the past sort of 5 or 6 years that are trying to measure the rates of growth in these protoplanets over time. For the next part of the work that I do, I have to actually go back and redo my title slide because what I'm going to show you aren't exactly images as you might initially consider them. I hope to convince you that they are indeed still direct detections at the very least, and maybe images if you choose to be a bit more liberal in your imagining. Because a big part of my current research is using optical interferometry, treating large optical telescopes as if they were radio dishes. Taking the light from all 4 of these, for instance, the very large telescopes at the European Southern Observatory in Chile, and combining them, the light from each of the individual apertures, interfering the light together and trying to understand something about the astrophysical scene. So this is a little bit more of a lesson here, but this is the young slit experiment. Where you have plane waves of light coming in, they diffract around 2 openings here. You see these 2 waves diffracting, and then they interferometrically, destructively combine, sorry, they destruct and they combine in sort of this coherent interference pattern.
Yeah, so
Results.
look at quantum mechanics and a macro wave.
Yeah, exactly, right. So this is the same principle as you know, interferometry with optical telescopes. If you'd imagine these slits not as slits in a sort of dummy experiment, but 2 telescope apertures, and then you have some optical path that combines the light from both of these telescope apertures, and then you put some camera here, you might be able to measure the interference patterns between these 2 telescopes. And really what you're trying to do with this is create a larger telescope when you have smaller telescopes, right? So with interferometry, you get the resolution element of a telescope that's the size of the distances between your 2 antennae, but you are limited by the collecting power that's the size of your smallest antenna. What this means practically is that if we use the very large telescopes as an interferometer, we can get a telescope that has the resolving power of a 130 meter telescope and still have the collecting power of an 8 meter class telescope. So this allows us to peer really close to stellar systems because we have such impressive resolution. And if we can beat down the contrast enough, we can detect systems like Beta Pictoris C. So this is the same directly imaged system that you saw previously that had a radial velocity signal that seemed to suggest that there was an inner planet. And our team looked at that with the gravity instrument, which is just one of the cameras essentially on the very large telescope interferometric array. And what you see here is that same interference pattern that's caused by the light from C and the light from A constructively and destructively interfering. So this signal here, these are actual photons, even though they're behaving like waves. These are actual photons from the planet Beta Pictoris C. It still screws with my head a little bit, so you'll have to forgive me. But if you do have questions about this, I'm more than happy to take them.
Victor?
Yeah, Victor.
You're on
So
mute.
don't you need don't you need phase coherency for
Yes.
interferometry? How do you do that with light?
So it's very complicated. We have to phase reference to something, right? We have to make sure that the light that comes in is properly phased up with the light from the other 3 telescopes. We do that with what's called a metrology instrument, which is basically a system of pulleys and runners that try and make sure that the light that's coming in down from the bottom of these telescopes into this command hub here are all properly aligned and all properly coming in at the same time, because the path difference from one telescope to the command center is different than the path difference here. We have to account for that in some way by delaying the light, with a sort of that path difference term. So that's done with what's called a metrology set that we use to phase reference. And then you want to amplitude reference to make sure that the flux that you're measuring is absolute in some metric, or at least relative to the host star. So there's a complex set of references that you do with the phases and the amplitudes of these light waves.
Thanks.
Yeah.
That's amazing. I know they did that. I know they did that
yeah.
with radio
Yep.
telescopes. I didn't know you could do that with light.
Well, so if it tells you anything about the difficulty of this process, they were doing it with radio telescopes in the 50s, and this is something that they had planned on doing in the 90s, and I've only really been able to sort of not perfect, but really been able to achieve in the 2010s, and now it's really hitting its stride in the 2020s. So it's an incredibly difficult problem that has lots of weird behavior. Sometimes I get data remotely sent to me from the VLT, and I open it up in the morning with a cup of coffee and I say, I have no clue what happened during this observation, and I have to put it down because there's so many contingencies and so many things that can go wrong in getting setups like these to work. But this is again some of the interference patterns of exoplanets and brown dwarfs that we measure with this instrument Gravity. And I'm part of a collaboration called the Exogravity Collaboration, who have sort of taken this instrument that was really designed to observe things like black holes and quasars, and we're repurposing it to try and observe exoplanets. But you can see here, these main peaks of the interference pattern are the locations of the source signals, and then you have the smaller amplitude terms off axis here. So what does this allow us to do? This allows us to measure the position of a planet with hundreds of times the precision of a single dish telescope. So these are measurements of the innermost system, the innermost planet in the 51 or the HR8799 system, HR879E. And you can see the error bars here for these single dish telescope observations, like the orbit movie that I showed you. Those are on the scale of maybe 1 to 2 milliarc seconds, right? So that's very impressive. Milliarc second precision is really, really great. It's what enabled me to do that analysis with the binary star. It's what allows us to say a lot about how stable these systems are. But with Gravity, we get something that's almost 200 times as precise as any one of these measurements at the micro arc second precision level. Something that this really opens up for us is that these observations are so precise that we're able to detect the influence that one planet has gravitationally on another planet. This is what blew my mind. This is work done by Sylvester Lacour, who's the principal investigator of the Exogravity Collaboration. This was a result that we published last year. We're able to, with this optical interferometry, detect the deflection on the path that one planet is inducing with the other. So this is the same Beta Pictoris system with the inner planet and the outer planet. And if you measure very precisely the motion of the outer planet over time, like this, and you compare it to what the orbit would look like if it wasn't being deflected, which is this dashed line, you see that there's some deflection around this that you can fit with another sine wave here. And that deflection is induced by this innermost planet. So this is the precision that we're able to achieve with optical interferometry. And this is something that's really, really exciting about this technique and why it's worth going through all of that, that hard work to properly phase reference these observations. So I recently submitted a proposal in the next cycle to try and search the 51 Aries system for a similar signal to see if there's some deflection in the path of this planet. And our team is investigating lots of these other directly imaged systems to see if we can't detect more and more of these gravitational effects that different planets are having on one another. And our hope is that we can find new planets by detecting how they're affecting the planets that we're already able to observe. Another great byproduct of gravity observations is that it also has a spectrographic component. So we can observe the spectra of the planet just as we're gathering these super precise astrometric observations. In particular, we can measure absorption of molecules like carbon monoxide and methane. And these can tell us something about the elemental abundances of the planet and help us determine maybe how or where it formed. If you think back to those protoplanetary disks and also back to Dominic's talk, a protoplanetary disk has different abundances of say, water when the water freezes out into ice versus when it is in its gaseous phase closer into the star. So if you can measure very precisely the abundances of these elements, you can kind of pinpoint where the planet might have formed within its parent protoplanetary disk. So this is something that was done for HR8799E. Here's an absorption feature of carbon monoxide within its spectrum. And they were able to measure the ratios of carbon and oxygen abundance and the ratios of the abundances of metals versus hydrogen. And these two clues were able to tell our team a little bit about how and where this planet formed. There's no big conclusive evidence yet because we still don't understand a lot about protoplanetary disks either. But we can start to build a narrative about the formation of these systems. So a little bit more of my particular work. I'm hoping to present a paper soon that studies a sort of brown dwarf near that twilight zone that is around the deuterium burning limit. And I want to try and measure these same molecular abundances in its atmosphere to be able to say whether it formed from a disk like a star, whether it has a lot of carbon and oxygen that were enriched by, say, planetesimals, or whether it formed more like a brown dwarf or a star from the collapse of a very uniformly abundant molecular cloud. And so these are just some preliminary observations with gravity. And this is showing you again where these objects lie within the sort of mass occurrence regime. And then latest of all this is a really exciting paper that I helped analyze on another one of these strange systems that has maybe a couple of planets, maybe a brown dwarf, none of which we're quite sure of, all embedded within a debris disk. So this system is really quite fascinating, and there'll be a paper published about it, hopefully within the next month or so, that should shine some light on what we think is going on here. But again, these are things that are just so completely different than our own solar system that we are breaking our notions of how systems form generally. And then I wanted to leave off, sorry, Phil, if I'm running up on time, but with some future prospects of cross collaboration between direct imaging and the other techniques. So the Gaia space satellite and radio velocity searches are soon to be dredging up detections of temperate and long period giant planets. The radio velocity observation baselines, these surveys that have been going on for 20 years, will start to pull in robust detections of planets like Jupiter. And Gaia will be able to very finely measure the influence that those planets have on the motion of their host stars throughout the night sky. And the hope is that these planets that are sort of in the middle of these two populations of detectability will really be what interferometric measurements like gravity cut their teeth on. So these systems will be the most similar to Jupiter and Saturn than any directly measured systems, and will allow us to compare those atmospheres to the atmospheres that we're able to study very finely within our own solar system, and tell us a lot about how solar systems form and evolve. I wanted to just give a brief plug. So I'm the Observatory Fellow at the Maryland Space Grant Consortium Observatory. We have our observatory here on the JHU campus, and if you're ever in Baltimore for one of our open houses, I'd love if you guys would come and say hi. We have a 20-inch telescope here that suffers from Baltimore seeing, but we still try our best to make fun observations of beautiful astrophysical scenes, just like the rest of you. So if you're ever in town, pop in. This is what I was doing last night. So thank you guys so much for having me, and I'd like to open it up to questions.
Arjun, I see you have your hand up, but I'm going to ask you to hold till we get through the meeting, okay?
Totally.
And Jim, because we got a couple things here. William and Dominic, if you could hang on for a while longer.
For sure.
We'll get through a couple of stuff, and you guys can hang to your questions there. So this was, let me slide you guys back over. So I'm looking at you here. So I mean, I don't even know what to say. It's just outstanding. And I'm going to pick back up here again with the rest of our meeting here, and then we're going to come back along. But William, that was, I'm kind of at a loss for words. It was just spectacular.
Well,
So
thank you
we'll
so
give you
much. I really appreciate it, guys.
the big hand there, and then we're going to come back to you with the rest of the questions. That would be, as otherwise, there's quite a few submissions here and a couple of things we want to cover. So let me share my screen now. And so once again, top speakers like Dominic and William tonight, they came from you guys. I mean, you were found by Michelle and by Bob, and Ken has created this speaker form, which is online, and to suggest speakers for the future. We do need a speaker for our July meeting, and we have some others already lined up. And it's been great. It's just really taken the pressure off of me, trying to find people. I always have had help, but this has now formalized it and made it a lot better than it has ever been, probably. So I'm going to turn over to Ken for a minute here. Ken, and you can talk about this and related topics that you might have.
Okay, Phil. I don't need to share the screen.
Okay.
But you guys can hear me, right? So as Phil mentioned, the main thing is we need somebody for July. July 21st in particular is the meeting date. So please, if you have anybody that you think might be able to do a presentation, which is only like a month away, please go to our meetings page, as Phil's got on the slide here, and right at the top of the page, there's suggest a speaker, and that's all. You don't need to remember any URL. Just click on that and it'll bring up the form. We do have our own Jim Tomney presenting in August on Jupiter, a big fun for the amateur astronomer. And we have for October and November, we have two speakers tentatively lined up. I don't want to announce their names until they're finalized, but we'll also need somebody in September. So July and September, July 21st and September 15th are the dates that we need. And I do want to say that I want to thank, there are 4 people already had used the speaker form to make suggestions, and we've reached out to all 4 of them. 3 of them have responded yes, and that's what we're coordinating with. But the 4th one we haven't heard from yet. But anyway, do what you can to try to find somebody. It can be any astronomy related topic. And that's it for now, Phil.
Thank you, Ken. And one thing I'd like to say to both you, Dominic and William, is that one is, please keep us in mind when you have new papers, new research, something exciting that's happened. You both know how to get a hold of me. Just drop me an email. And, you know, not, it doesn't have to be for one of these meetings. We haven't had a astro school for a while, but we do special sessions, and they're not unusual to do them. And if there's something coming up, we just throw it up whenever you're available, and whoever could join joins. And they've been very, very good. And so please, you know, keep us in mind. And to both of you and to our guests, you are more than welcome to join all of our meetings at any time, and you can become members of HAL if you want. It's, everything's right there on the website, and we would love to have you and to stay, you know, for all of you to stay involved. It's really a lot of fun. And so that's that. But thank you very much there. Let me click on the slide here, and then. So it's time to move into our submissions from all of you. This time, normally I block them by the people who submitted them, so you don't have to bump back and forth. But today we had so many that came in categories, and so many of the moon this time, which is really unusual. You would think it would be more common, but we had quite a few. So I've kind of clumped them in there. So I'll be jumping in and out to many of you at different times through the presentation to talk about your picture here. Once again, we have quite a few, so just try and keep it a little bit brief as you're describing them. And so Gene, I know you're on, right? Saw Gene earlier.
Yep, I'm here.
There you go.
So I was in West Virginia, and I wanted to try and get a picture of the tidal tails on M51. And for 4 hours of exposure, this is what I got. So you can see on the right part of it, to the right of the bright spiral part, you can actually see that extended tidal tail from the two of those galaxies colliding.
That's great. I see Jim Johnson's head shaking back and forth. He's in awe. So, and then, so these are all similar target here. Actually, it's not exactly the same, but Thorn put together a little grouping here that's pretty interesting.
Yeah, can you all hear me?
Yep.
Yeah, so I was out in, I guess, World 4 skies over out near Easton, and I wanted to, because it's pretty high up in the sky right now, so it's a nice one. So yeah, just got an hour and 45 minutes. These are 90-second exposures. Yeah.
You know, that's without the description there.
Yeah, I was excited that I didn't realize you can see those small galaxies, and yeah, that's my field of view.
And that was that. So Thorn,
Thank you.
Thank you. Back to you, Gene.
So this is from my backyard. This is the Edge-on spiral in, no, I don't remember the name of it, but anyhow, but big spring galaxy. I think this is one of the biggest Edge-on galaxies you can see that we can see.
Very nice. Yeah. And then we have some kind of scenic shots here. Hannah, you on, Hannah? I thought I saw Hannah.
Yes.
There you
Hi.
go.
Sorry, I'm here. Yes, I took this at Assateague State Park. I went with Connor for my birthday. We lucked out with just unbelievable skies that night. So you can see Sirius setting, you can see Orion's belt pretty close to the horizon. And although unfortunate, I do kind of like the added detail that the light pollution adds, but don't quote me on that. So.
Yeah, so. No, light pollution is going to be a theme in a couple of these coming up. That's great. So here's Gene, a Milky Way shot from you.
Yeah, so like I said, I was in West Virginia. I went out to see that Tau Herculid meteor shower. I was really hoping to get like a picture like this with 100 meteors on it. All I got was one.
We'll hold that. I got another picture for you to comment on that, and hold your thought there. And then here's what I did with my Canon camera on 15-second exposure, and a lot of other unique settings. Dave Zolette was with me, and a group of people that one, as well as Cheryl and some others. This was at Blackwater Wildlife Refuge. And I'm going to talk about a little bit about what's going on at Blackwater in the future here in a few minutes. So, yeah, so this was my shot. And then Jim.
Yeah, the planets are
Moving into
starting to,
planets now, so good.
yeah, they're starting to get out of the glare of the sun in the morning. So grabbed one of Saturn. You can see the rings are definitely closing up now. It's going to keep getting thinner and thinner as we go along. And Jupiter with the great red spot just rotating into view. So looking forward to the season. It's starting to ramp up as they are getting further away from the sun.
Yeah, it'll be nice because now James Willingham won't be asking me to open up at 3 o'clock in the morning anymore. So
yeah, it'll be 1 o'clock.
Yeah, there we go. And James, James, did you make it? Speaking of James, no, but James did submit. He wasn't sure he was gonna make it tonight, but here's some nice pictures of Jupiter and Saturn that James captured. Beautiful as always. And here's one he did of Mars. And then James, oh, so this was from James. Gene, I was thinking you should read, but so James was also frustrated like Gene was, and he called this the Tau Herculean meteor bust. So, and so he captured 2 in this image here. He sent it through. And then here's one of the conjunctions of Jupiter and Mars. Very nicely done. And Arjun, man, is stepping up his game.
Oh,
We've been watching Arjun from day one when he started, and here he is today. Go right ahead.
Right. So first of all, I hope Hannah isn't mad at me for sharing these images. She said she was going to use it for something else. So yeah, I'm sorry if I made you mad. But anyways, this image was taken with Halo. Thanks to Mr. Wayne for helping me use Halo. So this is an image of the Leo triplet. It was really low on the horizon. And yeah, this isn't the best picture of it because I was only able to get about 55 minutes of data. But I just thought that instead of processing it in terms of finding an asteroid, I thought I might do my usual artistic process. And so yeah, I just wanted to do my artistic process and see how it looks.
Got it. So just so everybody knows that Arjun has a challenge from his mom, that Arjun is his research project is he's trying to find an asteroid that has not been located yet with a very small telescope compared to the ones that are used for doing this for big time science. And his mom has told him if he finds one, it's validated, she's going to buy him whatever he wants for his hobby here. So he's motivated.
As long as he can lift it.
Yeah, as long as you can lift it, right.
Oh, don't get me started on that. It's a really huge problem.
Yeah.
But anyways, this is another one of my artistic process. This is the famous discovery image. Yeah, but off to the side there, I think you can still see the small streak of the asteroid. But in this, I heavily went on noise reduction, and I did background neutralization so that everything looks nice and noiseless, as people like to call it. So I really like the BF cluster, how it turned out on this one. This is plenty of data to work with. So yeah, this is better in terms of quality than my Leo triplet image.
Yeah, very nice, Arjun. Thank you. Moving to the sun, Mr. Johnson. Jim.
Yeah, this was yesterday or day before. Yesterday, there's lots of sunspots out there. This is white light, and about 6 or 7, 8 sunspot groups. AR 3032 was in the news for throwing off a big flare yesterday morning, and probably more to come out of that.
So taking Jim's lead there, I imaged in H alpha. Our orientation's a little bit different, but it's the same sun. Jim was looking at the photosphere. I'm looking at the chromosphere. And here's what it looked like. You see some beautiful filaments there, very, very large. And it's also interesting watching the patterns, as well as you have some prominences coming off the edge. Nothing too dramatic there for this one. If that CME had blown off the edge, probably would have left behind a really nice prominence. But here's so mine's blocked up here. This what I call the helicopter prominences. I like those. So, anyways, that's my shot of the NH Alpha at the same time as Jim took his. Now over to the moon. We have lots of moon pictures coming up. Mr. Connolly, looks like your backdrop. Mike?
Hey, everybody. Yeah, I just took this just a few nights ago. The moon was actually quite low in the sky, and it was kind of hazy out, but I thought this turned out really, really well. I was pretty pleased with it.
Yeah, it's nice when the moon is full like that and you have a little bit of haze. It actually helps with the contrast sometimes. So,
Really?
yeah, very nice.
And it also helps with the seeing because you won't have haze if the atmosphere is turbulent.
Yeah, right. That's a good point. And here's one from James. Back to you, Jim.
Let's see, that's the moon with a one-shot color planetary camera. The contrast, not the contrast, the saturation, I added like 6 or 7 saturation layers to bring out some of the surface colors. This is the, if you can see my, no, you can't see my cursor. Almost directly below the large crater just above center. It's come down to the mountain range and just a little bit to the right. And there's where Apollo 15 landed, down in there.
Oh, very nice. Great picture. Thank you. Hannah, artistic time.
So this picture and the next picture that you'll see by me, this was the moon taken during the star party. I had a little fun with it, just because I grew up around a lot of pop art, and I always like to kind of experience the moon in different ways. And I think, a lot of what the movement of pop art comes from was taking minutia and mass-produced things and stuff that you see every day and kind of taking another spin on it. And I thought, what better thing to do that with than the moon? So the moon did look really beautiful when we did get breaks in between the clouds. I don't think Richard's on tonight, but thank you to Richard for, we definitely bounced ideas off of each other and helped keep the ILIG going. So it was a lot of fun, and a lot of the Boy Scouts who showed up had a great time.
Thank you very much. For those of you who are watching this on YouTube, Hannah referenced the ILIG. That's the Leona and David ILIG donated the 6-inch Takahashi refractor we have in the in our observatory, so we affectionately call it the ILIG.
And then that's just another one. My mom was joking that I need to do 2 more and I can sell them in a set. So watch out, Marilyn Monroe. But yeah, I had a lot of fun with it. So, and I look forward to, finding different ways to interpret something that we see all the time. So
yeah, very nice, very cool. And that's it for the images. I do have a couple of announcements I want to make, and then we'll turn it back over to questions for William and for Dominic. A couple of things. One is last month, the month before, we had a presentation from Karen at the International Latitude Observatory in Montgomery County. And on the 25th, which is also a night for a members' star party, they're doing an outreach program there, and they're asking if HAL would like to participate in that. So I'll send out an email to the group, and if you're interested in going out there and bringing a scope out for the public, and then I'll connect you up with Karen, and you can work with her on the logistics and stuff. I'll send out this email to you guys. This Saturday, Robinson Nature Center is having an event you have to register for, but they're having an event to celebrate the summer solstice. And as part of that, they're doing solar observing and asked us to bring out our solar scopes. And last count, we have at least 7 solar scopes going out there, which will probably be about a scope for every 4 or 5 people because it's limited registration. And that'll be awesome. And then we have a couple more people coming out to support, Salgi and Hannah will be out there. So along with us with the telescopes. So that's from 2 to 4 at the Robinson Nature Center this Saturday. Also at the end of this month is the Green Bank Star Quest Star Party. There's 5 of us that are heading out to Green Bank. So if anybody else is going out, let me know. It would be nice to have all of us. Right now it's going to be myself and Bob and Joyce Dutilli, Gary Engel and Ken Eberhardt are going to be out there from that I know about. So those are the things that are coming up.
Phil?
And one more thing, hang on.
Phil, when is that Green Bank Observatory event?
The Green Bank is it starts on the 29th, which I forget which day of the week that is, maybe a Thursday.
Friday.
Right.
Wednesday.
Oh, it's a Wednesday. You're right. It's a Wednesday.
Yeah, and it
But
goes
yeah.
to Saturday.
Okay.
So, and the registration, just go look up a Green Bank Star Quest on Google. It'll take you to the link, and you go in there. And it's if you have questions, give me a call, because there's a lot of caveats there, because there's no wireless of any kind. There's no communication. It's the quietest place on Earth, and but it's a very good time. Bob and I and Joyce have been going for a number of years, and Ian has been out there with his brother Mike. So anyway, so that's it. And the last thing I want to talk about is that and I'll bring it to questions, is that I'm going to be sending out some information, but the Blackwater Wildlife Refuge has, where you saw some of those, where you saw my shot, at least with the Milky Way, they've installed a Celestron, a 12-inch Celestron out there on a pier, and it's going to be completely automated, and where the public can dial in and use it. And they're very excited to have HAL participate with them. So they're going to be doing some events out there, and they're going to open it up, outside the park, but at the visitor center there. And they'll be doing some star parties, and they'll ask us to support, and we'll get out there in those really night sky, really nice skies, some light pollution at the edge, as you can see in my picture before. But those are all the things that are going on, more to come. Somebody else have a question? Go ahead.
Yeah, go ahead. Victor, why don't you go ahead? You had your hand up first.
I have one more thing that's going on, and that is just letting everybody know, I will be heading out to Little Orleans campground this weekend with my telescope. So I'm going to be having a remote impromptu. So if anybody wants to go out there, I should be there Friday and Saturday nights, just letting you know.
Right.
Okay, and I wanted to remind everybody that before our next HAL meeting on July 12th, the James Webb Space Telescope is supposed to release their first set of actual full color science quality images. So keep that on your calendar.
Yeah, great. Thanks for bringing that up. Ken, you have something?
When you said about registering for the Saturday.
Yeah, that's with Robinson Nature Center.
Right. Did somebody say that was already full, or what?
Yes, that event is full.
Okay, that event's full. Okay.
Okay, so too late, huh?
Too late. Yeah, but you could come out as a member. I mean, we're outside on the roof, so the general public, whoever comes to walk the grounds and everything, will still be there. So the program itself is sold out, but we're outside on the green roof, right by off the front door there. So So hell, come on by, no problem.
All right, thank you.
Yeah. And next month, Victor will be running the meeting. I'm very appreciative of that. While he's running the meeting, I will be at Stonehenge. So I'll be completely the opposite on the astronomy history from where William and Dominic were today, taking us into the future. And I'm going back to the past, and I'm looking to come back with an interesting short presentation for everybody when I get home. So I'm very excited.
I was going to say, sounds like a September speaker.
Oh, could be, at least a portion of it. So so with that said, normally I would say goodnight to everybody and stay online and ask questions and turn off the recording. But I think I'm going to leave the recording running, because the people who might be viewing this for the length will be interested in these questions and answers. So once again, though, to formally end the meeting, I would like to say thank you to everybody and especially to Dominic and William. And it was just a really great night. I mean, really great. And I hope a lot of people watch it that could have been there. And with that, let's just open up the questions. You guys unmute yourself and ask away.
Question for William. When was the first direct imaging of exoplanet done?
That's a really great question, Bill. I believe that the first sort of validated direct image exoplanet was, most people would call it Beta Pictoris b. So Beta Pictoris b was first imaged in 2004, and then it was validated to be co-moving with its host star and orbiting in 2008 when it was published. There are a couple of other sort of, again, we're in the sort of oddball or twilight zone that I was speaking about. But there's a system called 2M1207, which was not always considered a planetary system, but is a system of planetary mass objects that was detected, I think, also in 2004. So around the early 2000s is when you're getting the first direct images of planetary objects. Yep.
William.
Yes, Bob.
Surprised you didn't mention TRAPPIST-1 at all.
Yes, well, sadly, TRAPPIST-1 is far too miniature to be directly imageable anytime soon, but I do have
5 years away.
Yes, I do have a fondness for the system. And I actually wrote a piece of journalism recently that previews all of the James Webb observations that'll be going on in the next year on the TRAPPIST system. So if you're interested in that, that's I think linked somewhere online. But that was an article for the Planetary Society. Yes, I enjoy all sorts of planetary systems, not just the directly imaged systems.
William, do you think we're going to find life on TRAPPIST on any of the planets?
That's a loaded question. I am far more pessimistic than I think even the average astronomer is. But and that's partially because I know just how difficult it is to measure these spectral signatures from my work on direct imaging targets. I'm fairly confident that Webb will be able to detect molecular signatures in a handful of the TRAPPIST-1 planet atmospheres. But whether that results in being able to detect biosignatures is really a function of how much time is allocated to future observations, and really how sensitive Webb is, which is an open question until we get all that commissioning data that's going to release in the next couple of weeks. So I would hold out on truly answering that, but I'm very skeptical. I think maybe the next generation space telescope, that's a very big possibility though.
You mean Nancy Grace Roman? I mean, is that the one you're talking about? Or LUVOIR?
I'm thinking LUVOIR, more the 2040 sort of next flagship. Yeah.
So William, here's a little bit of an off question. And Dominic, maybe you even have an opinion if you're still on. There you are, see it there. So, that's the elusive planet X right here in our own system, right? So here we've made this tremendous leaps in not only finding exoplanets, but now imaging them. And yet scientists have determined that there might be a planet X out there because of the gravity and everything else that's known. So, what's your guys' thoughts on why is it so difficult when that's kind of like using a magnifying glass as opposed to a giant telescope? You're on mute.
That's a really great question. I think that the primary difficulty, right, is that there's a disconnect between survey quality instruments and really deep imaging instruments, right? The fields of view of the James Webb Space Telescope, imagers of GPI and these other instruments are really, really tight. And so it makes, large scale surveys for something that could be really anywhere in the ecliptic plane incredibly difficult, like Planet X. And then you do have, I mean, a lot of really great survey instrumentation that's coming online that's been operating for the past couple of years. But really the only thing that's sensitive in those wavelengths that we think Planet X would be brightest is maybe the WISE mission, which was a 40 centimeter telescope in the mid 2010s. You know, maybe Spitzer, some of that kind of stuff. But so I think that's really the primary reason, is that there's a large sky, and the survey instruments that we have right now aren't as deep as would be necessary to observe Planet X. But that's something that could change very rapidly, especially with surveys like the Vera Rubin telescope, which is an 8-meter survey class instrument that's coming online in the middle of the decade. Yeah.
Thank you. Anybody else?
Question. So thinking about in terms of life, could you find a ratio between the amount of sunlight falling on the Earth and apply it to other solar systems and see if they match?
Yeah, so that's going back to this habitable zone concept that I think you hear being bandied about a lot in exoplanet science. There is that sort of basically the relationship between the insolation, or the amount of photons that a planet is receiving, and its distance from its host star, and that has some degeneracies with the brightness and the size of the host star itself and the size of the planet. But when you put all those together, and those are relatively easy equations to link together, you can come up with a scaling relationship that tells you where around a certain type of star a planet would intercept light that is similar to the amount of light that the Earth intercepts.
Okay, so going back to my question on whether on dust, which is between
Totally.
yeah. So going back to that, could the telescope which you're using change its pixel scale or change its mirror deformation to account for a higher contrast when there's dust in front of the planet?
That's a good question. I think we're at the point where we're really trying to give every observation all we have, if that makes sense. So there's very few instances, at least when we're imaging these very faint exoplanet systems, where we're not refreshing our deformable mirror at the highest refresh weight that we can manage, or where we're not trying to squeeze every last bit of contrast out of our pixel scale, out of the instruments that we use. But the dust question that you bring up is something that's really concerning, especially for there was a question earlier in the talk about visible light observations. So dust in infrared light isn't too big of a problem. It has its own emission component, but usually it's so diffuse that it doesn't obscure bright protoplanets too badly. Caveat there. But in visible light and in reflected light, say for instance the Nancy Grace Roman telescope, which will attempt to do some direct imaging for the first time in reflected light, we don't really understand how much dust is in most exoplanetary systems and what that effect will have on the observability of the planets in those systems. So there's a lot of simulation work going on at Goddard and at APL right now, where people are trying to test the observability conditions when you have X amount of zodiacal light in an exoplanetary system. We have one reference point in our own solar system where we have a zodiacal light contribution that we can measure, but we don't know whether there are more or fewer planetesimal collisions in other solar systems that generate more dust. So your concern is very valid, Arjun, I would say.
Okay, thank you for answering my questions.
When you talk about the contrast,
Totally.
the 10 to the minus 9, 10 to the minus 10, is that just in the infrared spectrum, or is that?
That would be in the infrared. In the visible, you actually get a little bit of an improvement if you have a favorable phase orientation for something like the Earth, which reflects has a higher albedo. If you have an even higher albedo body, then you can get favorable contrast there. The difficulty in that respect is that the atmosphere is far more turbulent at shorter wavelengths. So it's much harder to correct for the atmosphere using adaptive optics and achieve a stable enough image in visible light. Which means that, you know, if you have these big telescopes, you're not achieving their full potential. So if we had, say, you know, a very large visible telescope in space, then definitely we'd want to go to visible light to observe those reflected light planets at a more favorable contrast. But we can't put a single dish visible light telescope of that size, you know, to make that sort of optimization scheme work out in our favor. So yeah, that's very insightful.
You know, I noticed during your presentation, you spoke quite a bit about contrast.
Yep.
And I only heard you mention resolution one time when you were cranking through that, the images that show how sharp the pictures were.
Yes. Yep.
And is contrast and resolution in this sense almost interchangeable in the way that you're talking about? Because
yeah, in some sense, right? The closer that you get to blending those two point spread functions, the sort of greater the contrast that you have to achieve to, you know, pull one signal out from the other. But the reason that I didn't speak too much about separation is that that's just not a problem that we can solve easily except by building bigger telescopes, right? And so for the, you know, class of instruments that we have right now, we're limited in some, you know, very real way by to a certain, you know, regime of separation space. So really the extent that you're seeing on that plot is of, you know, the directly detectable objects. That's the extent of separation space that we can access with anything that we're doing. The exciting thing about gravity is that we can sort of push in a little bit further with interferometry, but it's only when we start building new telescopes, which is sort of slowed recently for mostly funding reasons. When we're able to have larger apertures is when you'll see new separation regimes opened up.
Yeah, because when you talked about that one area where you said you're having a hard time getting your head around it.
Yeah, yep.
You know, when you talk about what a planet, how it's structured, what it looks like, if you will. And, you know, it's amazing to me that you could separate as much detail as you already can.
Yeah.
Basically a couple of pixels and a blob of light, you know, if you will, whatever the wavelength.
Yep.
And to be able to start saying, well, this has, you know, this percentage of liquid, some kind of water, some kind, and this much land mass and everything else, that's going to be resolution, right? Eventually.
Yeah, that's very true. Yeah. And you know, interferometry is one of those, you know, fascinating fields where the impossible was, or what we thought was impossible, really turned out to be possible. At least, you know, at the start of interferometry, we were thinking, okay, maybe, you know, we can start looking at the brightest things at some, you know, nice resolution and get good images. And then when you turn these, you know, interferometric telescopes online in the 90s, suddenly you have people resolving the surfaces of other stars. You know, there's a handful of nearby giant enough stars that we have maps of, you know, not of them as point sources, but at the full disk of the star interferometrically mapped. And to imagine doing something similar like that with a planet, you know, one day, that's when you're really getting out into speculative space. But it's something that is just so exciting about that technology that even that you could speculate, you know, one day we could map the surface of one of these planets is really what keeps it special.
Hey, Dominic, and what's up next for you? You know, you're going to UMBC. Your high school career is over, completely over. And, you know, you're now, you kind of go into a lull mode where you're becoming a college student and you gotta go there, or are you going to college with a mission already started or in mind or an objective?
I'm a little bit in a lull mode. First year physics major is, you know, mostly first semester is just standard classes with like one physics elective and just a outliner of a C+ course or something. And then I was looking at my course load, and then fourth year is physics, 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 and then physics elective, physics elective, physics elective. And it's mostly optical holography and, you know, like atmospheric physics and solid state physics electives. So, you know, I've sort of got my full plate in front of me. But UMBC offers, you know, for master's courses, they offer an astronomy minor, but for just a bachelor's, they offer a lot of nice astrophysics electives. So that's kind of what I'm anticipating that I want to do there specifically. And then I was looking, actually, Dr. Prem, after I ended up winning the competition, she was like, this is probably good enough to publish. I don't know if you'd be interested in a little paid position at APL or something. So yeah, I have a little side question for William. I know that there's some research being done, I think at maybe from a guy at APL. I'm not sure where it's being done out of for a double coronagraph. Do you think that technology is going to be viable enough in the next few years that we could do some direct imaging in binary systems?
Yes, so that's and that's especially interesting because a lot of people are very fascinated in, say, Alpha Centauri and, you know, and these other binary systems. It gets really messy. I mean, just the pure math of it gets really messy really fast when you have off-axis components of these optical paths. But it can be done. There are smart enough people. So I think that and we have enough telescopes around the world that you should start seeing tests of those kinds of binary coronagraphs, you know, on sky, on sort of 4-meter class instruments, you know, within, my hope is within the next 5 years. I think that should be something that's pursued. But yeah, that's very fast. I need to look up who at APL's getting up to that. I haven't, you know, I'm only first year here, so I haven't gotten so integrated into all the different campuses. But what I should say to Dominic is that that's fantastic that your advisor is offering to publish so quickly. And I mean, one of the things that really allowed me to get into doing astronomy research, even as an undergrad, were summer opportunities like the one that you already, you know, had access to. So it's very viable to you know, be doing astronomy research, bona fide publishable stuff from Arjun's age to your age to my age. So if this is something you're passionate about, I mean, it's something that you're damn good at already.
Dominic, I did physics and astronomy in my undergrad, and I recommend, I don't know if your school has it, but if there's a branch of the Society of Physics Students, SPS, I strongly recommend joining. They will make sure that you get to go to all sorts of opportunities, conferences, special networking events, and it's all free as an undergrad. So I highly recommend, it's called SPS, especially for starting out as a physics major. It's a great resource.
Yeah, I think there's only maybe 80 students in the major I'm going into at UMBC, so it's
mine was 60, so it's a very small major no matter where you go.
Yeah,
mine was 3.
Yeah. Well, we started with 60. I only graduated with one other person. So yeah, it's a pretty small major.
Go ahead, Arjun. You don't have to raise your hand.
Okay, so the reason that I chose a refractor is because I didn't have to deal with collimation. So I'm sure that you guys don't use refractor telescopes because I've heard that it's not very good for like photometry and stuff like that, stuff like what you do. So how big of a problem is collimation? Do you have like some sort of auto collimator not available in the market, which you guys like use in order to make your contrast a little bit higher?
Yeah, that's a really good question. So most of the observatories that I work on have pretty complex focusing and collimation systems that are in place, and it's not. I admit my own ignorance on them because they work so well that you know, through most of my career, I just show up and the observatory tech has already, you know, sometimes if they're really nice, they've already taken your flats for you. And that's when you have to buy them, you know, chocolate at the end of the observing run. But usually there are people whose whole lives are dedicated to just that, to, you know, perfectly aligning and collimating these instruments.
So Arjun, you're gonna
They get paid well.
Arjun, you're gonna find out that that when you have a permanently mounted telescope, it doesn't require, now I'm not talking about, somebody who's looking for exoplanets with that kind of, need, or even what the, how other telescopes, work. But when they're permanently mounted, they require a lot less collimation. And even you could talk to the folks here in the club that have reflecting telescopes, that they don't have to collimate very often, even when they're moving them around, back and forth to the star parties and stuff like that. Just other than a test. Wayne is a really good person to talk to because he's always making sure his collimation is right before he goes into imaging sessions. And that's where it's really more important. I mean, when you're visually observing, you want it there too, because you want nice round stars. You don't want, trailing, oblong stars at the edges or anyplace else. But and Jim's, got both reflectors and refractors. So it's the right tool for the right job. So there's a place for both of them, but don't ever be scared away from using a reflector because of collimation. One is it's easier than it's ever been on modern day telescopes. And the other thing is, like I said, when it's a permanently mounted one, whether it's in a home observatory or a professional observatory, they don't get bumped around and jarred around. So once you set them, they're pretty much set except for tweaks, not major adjustments.
If I can add on to that as a reflector telescope owner, it's not like one of those periodic maintenance things where like I keep a calendar of it. It's like if I notice there's an issue with it, I collimate. If I see a noticeable issue, I collimate because I just do visual stuff. And then if I just bring it out of the bag and go like, you know what, it's probably about time to collimate, and I do it. But it's not like one of those like this is quarterly, this Q3 time to collimate thing.
I would add that it's awkward at first, but there's a learning curve. After you get past the third, fourth, fifth one, it's like falling off a log.
So Arjun, something really important here. People always ask what's the best telescope, and the answer we always give is the one you're going to use. So if you can't lift it, it doesn't matter how high quality it is. If you got to move it, you can't lift it, then forget it. But the point here is, though, it's really important when you're investing in a telescope to understand what you want to do with it, because the best telescope, the best refractor would be a very poor decision if you need to get a lot of photons. Okay. And the other thing is, if you want super high resolution, and the best telescope may not be a big mirror telescope. It might be even a smaller refractor, which is going to give you spectacular views of things where resolution matters. Especially, we show pictures these we can, but there's plenty of people like myself who are primarily eyepiece observers. And, so you got to know, that's why people have multiple telescopes, so, you bring the right one out for, what you're going to do with it.
The same is very true of research grade instruments as well. I mean, it's the reason why we haven't torn down most of the observatories that exist in the world today, is that, those 1 meter telescopes, the, 20 centimeter telescopes of the world, those are really good at, doing certain things and can still produce really fantastic and important results. The first exoplanet wasn't discovered on some crazy, telescope. It was on I think a 2 or 3 meter class instrument, right? So there's always a tool for the job. Although I do want to get tenure one day so I can buy one of those Takahashis. You can't get those on a graduate student salary, unfortunately.
Well, good night. And thanks, William, for coming.
Yeah. So what I'm going to do, guys, I'm going to thank everybody. I'm going to
thank you guys so
end
much.
the meeting and stop the recording. And thank you both for such great presentations. Everybody who participated and hang in here at the end. So now I'm going to, so as soon as I can find where to stop the recording, there we go. Good night.
William, are you willing to talk to my students?